Afternoon, my name is Jimena Jacobo, and I'm going to talk about the contribution in catalysis on the transition metal single atom of zinc oxide 000-1 reconstructed surfaces. These are the main points that I'm going to mention during the presentation, the poster presentation. I'm going to start by talking a little about zinc oxide. The zinc oxide can be described by the stacking consecutively of hexagonal layers of oxygen and zinc, which give us two unstable polar surfaces, one with terminations of zinc in the direction of 000-1, and in the opposite directions are a termination of oxygen. And it has been found in theoretical that the surface with periodicity 2x2 of the zinc oxide with an oxygen vacancy is more stable than the surface found experimentally with a periodicity of 1/3. And yeah, it has also been found that the zinc oxide surface is a good base for adsorb, and so that you can absorb like metal transitions, so you can improve the catalytical activity. It has also been found that the platinum group of metal transition is one of the best metals to improve the catalytical activity. And this was said by Chianelli. In the recent years, the single atom has been increased the investigation because it has proved that make more selective active points for the catalytical activity and reduce a lot the cost of the material, because I only use one atom instead of big amount of elements. And yeah, well, my job, I decided to obtain the surface of zinc oxide with a periodicity of 2x2 with an oxygen vacancy. Here is the oxygen vacancy. And I decided to adsorb like in points of high symmetry for different metal transitions. In my case, were platinum, palladium, ruthenium, and rhodium and ruthenium. From the 10 places that I adsorbed the metals, I only obtained like 9 stable places. And from these 9 stable places, I decided to choose the ones with the lowest energy that I mark here in red. And yeah, well, of the 34 surfaces that I obtained, the one with the most stable surface were the one that I adsorbed with platinum in the oxygen vacancy, which was the expected result, because I hope that it is known that the metal transitions have tendency to adsorb on oxygen vacancy. We try to get the most experimental, like simulate the most that we can about the experimental situation. So for this, we grab the platinum atom and change it, commutate it with a zinc atom to obtain a different surface. And once we obtain this surface, we leave off the zinc atom, and we decide to compare these 3 surfaces with the one that we obtained without any transition metal adsorb, and see which one was the most feasible to obtain experimentally. For this, we use thermodynamics. We use the surface formation energy. We use oxygen conditions because these can determine if our surface will get vacancies or adsorb oxygen. In this case, we get that the surface where we only absorb platinum, we're the one with the lowest energy in both conditions, poor oxygen conditions and rich oxygen conditions. Then the next one that was stable was the surface without any metal transition adsorbed. And the one that has the most unstable or is less feasible to obtain is the one that we change the atoms in the surface. And the platinum with a zinc vacancy, it's possible to obtain, but it's not the best option that we have. And then we decide to compare the one that we have the most stable surface with the combinations of the other three elements. Here we can see that the one with palladium have the similar single atom adsorbed in the oxygen vacancy, while the rhodium didn't absorb in the oxygen vacancy, but was close to it, which is kind of relevant. Like, it's like a sign that this area where the oxygen vacancy is relevant, while the ruthenium was the only one that didn't absorb near the area of the oxygen vacancy. It was quite very far away. It was between a bridge between two oxygens. And we again compare the surface formation energy, that obviously the platinum was the one with the less energy, and then the palladium followed it. But the next was the closest one with rhodium, and finally the ruthenium was the only one that clearly wasn't a possible surface to obtain experimentally. Finally, well, we tried to get the improvement of catalytic activity. So we use the isosurfaces to be able to observe if it was possible to absorb a molecule. And we can see that the platinum and palladium are almost the same, have almost the same isosurface, with the single atom being the most positive electrostatic potential, which can make possible to us to absorb electronegative molecules, while the rhodium has a kind of positive electrostatic potential, but isn't as positive as the other two surfaces. And the ruthenium it's clearly not possible because it's more neutral and is quite close to oxygen, which can make the molecule that we plan to absorb to break it down. And yeah, as conclusion, well, we achieved the purpose to obtain the theoretical model of zinc oxide 000-1 reconstructed surface with a single atom of platinum trapped of a molecule of carbon dioxide. We are still working on that to trap the carbon dioxide molecule, but yeah. But we know that it is possible because this molecule is electronegative. So we are hoping to get good results. And in addition, well, we get a new surface that opens a new area of research because it hasn't been found that platinum and palladium surfaces on zinc oxide. It has been found other elements like copper and gold and silver. And yeah, that's all. Thanks for your attention.
Thank you so much. The floor is open for the questions. Anyone having the questions? Thank you so much. I can't able to see any questions. So thank you so much for your